This is the solution to question 6 on the Cauchy's integral theorem tutorial sheet. The question asks us to compute the integral of 1 over z cubed plus 1 over the contour C, where C is the quadrilateral with vertices at plus and minus a half and plus and minus a half I. So the first thing is we draw out the contour C. So we're going to split the contour C into 4 different sections. So let's label the points a half I, minus a half, and minus a half I in the Argand diagram. In 4 sections we can actually parameterize the first section as a half 1 minus t plus a half it. The second section we can parameterize as a half I 1 minus t minus a half t. The next section we can parameterize as minus a half 1 minus t minus a half it. And finally we get the final section which links us back together. So we have a square, and in each particular case the value of t goes between 0 and 1. So we now know what our contour is. The standard procedure for trying to calculate the integral is to work out which points where f is not analytic lie within inside the contour. So we need to do a bit of algebra before we can work out which points of 1 over z cubed plus 1 are not analytic and lie within that particular contour. So firstly, we can factorise z cubed plus 1 as z minus 1 multiplied by z squared plus z plus 1. Now, from level 2 material, we know that this is equal to z minus 1 times z minus w times z minus w squared. And in this particular case, w is the cube root of unity. And this is something that you met in calculus and linear algebra. So w is minus a half plus root 3 over 2i, and w squared is minus a half minus root 3 over 2i. So now we use partial fractions to split the 1 over z cubed plus 1 into 3 linear factors. The factors on the bottom are z minus 1, z minus w, and z minus w squared. And if you follow through to try and calculate what a, b and c are using level 1 material, which you should be familiar with, you get the expression on the right hand side. I've deliberately left w in the answer because it saves us having lots and lots of pointless algebra floating around, which, as you'll see, is totally unnecessary. So, as I said, w and w squared are just going to be complex numbers, the complex numbers listed above. And I haven't written them out, although it is possible to make simplifications for reasons that will be apparent in a second. So that entire integral can be split up as 3 smaller integrals. Now remember, we're integrating each of these with respect to z. So this w is just a constant number. So the first integral is not analytic when z is equal to 1. The second integral is not analytic when z is equal to w. And the third integral is not analytic when z is equal to w squared. There's our diagram of the contour. Now the point z equals 1, that's not contained within the contour. So therefore this first integral has no points where it is not analytic within the contour. Similarly for w and w squared, both those points lie outside the contour. So all the problem points, the problems that would cause issues when we try to evaluate this, are outside the contour. So we now have 3 functions, 1 over z minus w, 1 over z minus 1, and 1 over z minus w squared, all of which are analytic within the contour of the integration. The contour is simple, so by Cauchy's integral theorem, each integral is going to be 0. So that means the overall integral is equal to 0 as well. And in fact, If we change the contour so that none of the points 1w or w squared are contained within it, then the value of the integral would change. But if I change that contour so that I always avoid z equals 1, z equals w, and z equals w squared, the value of the integral will still be 0.